It's, this is so that people can see a real world calculation. This is a real world calculation. It's a potential to emit. And they'll do either the cylinder inside or they'll do the sleeve of the cylinder, depending on which part of the compressor they're working on.
Do they give a wall thickness?
Yeah, it's the 0.04 inches.
Okay.
That's what you're removing. Yeah, it's the 0.04. So that is an actual real world calculation. All right. So we're getting started. A couple of things, just a reminder, you've got, I think it's till noon today to get your memo in for the book report. If you haven't come by and done your planner presentation, your time is starting to run out. I will not be over in Enid on Friday. So I will be on Enid on Friday, November the 22nd. So I'm going to be there all day. So those who haven't done it over in Enid, please do so. Let's see. I've seen all my baseball players, right? Out of here. Well, yeah, you're not in the situation for next year or next semester. You've already taken engineering and physics.
It's a fun time. 10 out of 10 would recommend.
But for those of you who are dealing with schedules and looking at schedules, if there is because I know the Tuesday conflict is a conflict for baseball, and I know I don't have everybody who needs to be in engineering physics next semester already come through. Have them come talk to me, because our sequencing for engineering physics is such that we do it in the spring and we do it over the summer, and then we do engineering physics 2 in the fall. So you don't want to get out of sequence, because that puts you a whole year behind, and we don't want that. Also, if you guys know, because I know I've got groups and different things, if you are aware of somebody who needs to be in differential equations, holler at me, because we hit the magic number yesterday, and I'm working with math to get that one fixed for differential equations. So I think we're close on everybody who needs differential equations next spring, but I want to make sure that we're there. And please double check, because I have actually worked with several folks that have put themselves into double classes that they don't need. And that's one of the things that we want to make sure that's taken care of. So from an enrollment point of view, it's time. We need to get those kind of things finished up. For this class, where we're at, just so you guys have keeping posted here. I'm going to go back. These last chapters, even though we haven't necessarily gone over them as in detail, I am going to kind of cover a few things today using the author's PowerPoint, because most of these chapters in the second part of the book are on engineering fundamentals. They're kind of introductions to the various things that one calculates, length units, fundamental units, some of the basic things that you'll see in terms of heat, some of the basic things that you'll see in terms of material selection, some of those kinds of things. And so it's a nice introduction. So the homework is posted in here, chapters 10 through 12. You'll notice that it's going to be a relatively light week, and we're actually kind of winding down. The last two things that we will end up doing in here is I will have an Excel assignment, using Excel to do some calculations. So if you want to do this particular calculation in Excel, so that you could calculate it for a variety of different metals, putting in a different density, for example, that's good practice for you. So that's one thing that's left. So we actually have this class, next week's class, the week after Thanksgiving's class, and then the final. I've already made up the final. The final has 20 questions on it. Your midterm is a very, 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 very good study guide for the final. And some of the things that will be on the final out of these last chapters will be things like, well, give me some fundamental units and what their examples are. give me an engineering failure and why was it important kind of thing. So they won't be too difficult. The last several questions, which are high point value questions on the final, you're going to have to defend your answer, and it's your defense that's being graded, not your specific answer. Okay? So for example, if we say that, let me come up with, let's see. Let's say that there was a book that wasn't currently on the list for the book reviews, and you wanted to challenge that book should be included. Giving your reasons and how you state your reasons is what you're going to be graded upon. Okay? Not which book it is, not which field it is, not which, it's whether or not you were able to defend your answer. That's what you're going to be graded on those last ones. So just be aware that those are there, and those are the high point value ones for the final. But the final is Tuesday of the week of the week of finals week. It'll be, I think it's at 8 o'clock. Yeah, it should be at 8 o'clock, and we should be able to get it done there. And I should have the finals. I should have all my finals over in Enid on the 22nd, because I have gotten all my finals already made. So that tells you how close we are. That tells you how close we are. And then I did get all the lecture videos posted yesterday. Finally got all those things posted yesterday. So some things to kind of look at when we're talking about units and we're talking about tools. And our book is a really good book for giving you a lot of a smattering of different things, a lot of introduction materials. And when we talk about fundamental dimensions, length, time, and mass, they're fundamental dimensions. Area is going to be a derived unit. Volume will be a derived unit. So our fundamental things, length, times, and mass, we do have another one that they don't talk about here, but that's charge. We do have another fundamental unit that's charge. And then we usually end up getting a variety of different properties, substances, calculations that we're going to use those fundamental units. And we use dimensional analysis. Temperature is a weird one, because temperature is kind of relative. It's not fundamental per se. We do define temperature in terms of Kelvin as a fundamental quantity, but temperature comes and arises from the zeroth law of thermodynamics. It's really not what we're wanting to get at when we deal with temperature. What we want to get at when we're dealing with temperature is that exchange of heat. And that's what we're really after. So it's a little different. Temperature's a little different. So we get a variety of units, and that's why the tables in our book are great. This also violates PowerPoints, and I did not make this PowerPoint, but it does violate PowerPoints because it's very difficult to see. We got a lot of information on there, but we use these things for a variety of aspects. But this is a nice chart in that it relates the fundamental units to specific engineering factors. And if anybody ever wants to see it, I actually have a book of engineering conversion factors. That's all it is. And it has a variety of different engineering from a variety of different things, like hogsheads. Yes, hogshead is an actual unit. Fortnights are actual units. So you could get some really strange units for a variety of reasons. Hogsheads happens to be in the brewing industry, and it's a leftover. There's like 3 hogsheads to a keg, or something like that. 3 kegs to a hogshead. Something along those lines. It's an actual word for a different type of barrel, is what it is. So, and then there's barrels, and then there's barrels, and then there's drums. Okay. A crude oil barrel is 42 gallons. A drum is 55 gallons. So you can get some really strange conversions that's based off of what you're looking at and how the terminology is, which becomes very, very important that you know what you're dealing with. Okay? Because a barrel in one person's industry may not be the same as a barrel in another person's industry. And the other thing is their units that they actually use. Because you may get an M to mean 1,000, or you may get an M to mean 1,000,000, or you may get M to mean mega. So you have to actually really, really watch it when you're looking at units and using the common units for the industry then which you're in. So this one we're starting off with this chapter, and we're talking about forces. Forces you're going to get in engineering physics. And so why do we look at forces? Well, there's a lot of different things that are happening when we're dealing with structures and how we're going to balance out those structures. Also, forces, which we don't really talk about until you get to material property, like this morning. We're out there and we're looking at the forces on our engines, and we're looking at the forces on metal, and when it's cold, things have different properties. They may be brittle, and brittle is not necessarily good. You know, brittle's not necessarily good, but in some cases brittle is good, depending on which way you're wanting to look at it. So if we're dealing with force, that's this chapter. We're dealing with force, we want to look at that. We look at our forces, and it's our interactions between two bodies in direct contact. And so you can actually apply a direct force. Now remember, there's two types of forces. And we'll get into this. There's the direct contact force, like what you're seeing here. And then there's a field force. Field forces are like gravity, where you can have a ball above the surface of the earth and you let go and it's going to go to the surface, or it's going to fall. Or you've got two charged particles and they can either be attracted or repulsive. You've got a magnetic field that you'll go in and have things that are out there. So our forces that are going to be in there. But when we get into engineering, where the force is applied and how we move those forces around when we actually do the calculations becomes very important. Because we will get different things that we have to look at whether or not we're going to get torques, whether or not we're going to get stresses, whether or not we're going to see different pieces. But we can shift forces around. Statics, engineering statics and engineering dynamics. Statics is all about maintaining equilibrium. Dynamics is when we put things in motion. So this is, you start out with, and that's what we typically do. When we do engineering classes, why on earth do you have to take general physics? Well, or engineering physics, or whichever physics it is. Those are the fundamentals, okay? We're going to give you the language of what it is we're looking at, and we're going to give you an overview. And when you hear it, I'll tell you we lie to you. We lie to you all the time. We lie in the sense that if you're in physics class, how many states of matter are there?
33.
Physics class.
4.
Thank you. Physics class, there are 4 states of matter, sorta. Chemistry class, how many states of matter are there? 3. Sorta. Right now there's an argument, is there 9, 11, or 13 states of matter? So we lie in the sense that in a general overview course, we're going to simplify things. We're going to simplify things. We're going to give you Newton's laws. Newton's laws work really, really well for certain conditions. The ideal gas law works really, really well for certain conditions. But they're not perfect. And so we introduce the concepts in a general course. That's what we usually do. Then you get a sophomore or junior level course, depending on what the topic is. So in engineering physics, we're going to learn about forces, and we're going to learn about the conditions of equilibrium. Then we're going to give you a whole semester class on the conditions of equilibrium. We call that statics. We give you a whole semester class on when we put that in motion. We call that dynamics. Then you might get, you might get a sophomore level course that is looking at classical mechanics. Then you can get a graduate course looking at even more classical mechanics. So what happens to us is we give you an overview course to give you some basics, to give you actually the language that you'll work with, give you some fundamental concepts. Then you end up taking a deeper dive and looking at the consequences of all those things. And you look at it in more complex situations. And as you take the next level course up, you get even more complex situations. And you get more specialized. So for example, if I'm doing things in equilibrium, well, it's all well and good to know what things are in equilibrium, but then I really need a strength and materials class to understand how that equilibrium is going to play out if I have I-beams, or if I have concrete beams, or if I have carbon fiber. Because in the case of carbon fiber, the tensile strength of the material is very, very different if I'm along the fiber or if I'm perpendicular to the fiber. So we get a lot of different pieces to how we dive in, and then as we get deeper and deeper into those calculations, instead of a 2-body problem, we deal with a 3-body problem. Or instead of a 3-body problem, we deal with a 5-body problem. Or in the case of statics, we do it in 2 dimensions and then we do it in 3 dimensions. So we do have a lot of things as we start diving into what's happening. We look at it at various different levels. So when we say we're applying a force, sometimes it's pretty clear and easy where that force is being applied, sometimes it's not. And the direction of the application of the force can also be a huge impact on not only the material, but on the interaction that we're ultimately going to see. So that's where we're headed. So you can do things on tendencies of force, and this comes really fun, because not only do we get bending, twisting, elongation, compression, we can also have a force that causes us to do translational motion versus rotational motion. And if you think about it, just the act of rolling a can down an inclined plane. If I take a can and let it slide down an inclined plane, it's going to have one behavior. That's strictly translational motion. But if I take a can and I let it roll down the inclined plane, I'm going to get a whole set of different behaviors. And that's why we start looking at the various aspects that we have in engineering. So we get some tendencies for force. So you've got a whole chapter on forces. See if I've got one. And there's our, the Newton's laws. We get our reaction forces. Let's go over here. Then we get things that go like pressure. And pressure is going to be different. Well, pressure's not different. Pressure's force per unit area. I don't care what I've got it in. But how we utilize pressure is going to be very, very different than if I have a solid or if I have a liquid. Actually, it's not even a liquid, it's a fluid. But if I have a liquid, liquids are incompressible, or they tend to be incompressible, which allows us to have hydraulics. Now, liquids do have a little bit of compressibility, but in the idea of hydraulics, that's not a big issue. So we do talk about pressure, and pressure gives us a whole lot of different things that we start working with it. So that's force acting over an area. Other things this is where we get into common units. Because most of us don't work in pascals. Very rarely do we work in pascals. At least not here in the U.S. We're working at PSI or PSIG. PSIG means gauge pressure, because that takes care of atmospheres. We still work in millimeters or inches of mercury, even though to buy a barometer that has mercury in it now is very, very difficult to do. But we still use those units. But we do PSI, and we do pounds per square feet, and we do a lot of those different units, and we do pounds per square inch, and we have so pressure becomes. But it's Pascal's law that allows us to have hydraulics, and hydraulics makes our work a lot easier. And we get strange things that we can affect the hydraulics by using strange types of fluids. We can use electrical rheological fluids, and those are fluids that are impacted by an electric field. or we can use ferrofluids, which are fluids that are impacted by magnetic fields. And ferrofluids are really good for certain seals, for certain different things, because we can hold them in place by using magnetic fields, and we can change their character by applying the field to them. So electrical rheological fluids and ferrofluids are cool things. And so you can look at Pascal's law. We get our buoyant force, we get atmospheric pressures, and we get our various units of pressure. And I'm going to come scrolling down here. We get material. So let's look at a hydraulic system, just for funs and giggles. Hydraulic systems say my force per unit area, the pressure throughout the liquid has to be the same, and so I can use it for pistons. So things like doing the scales when I take a semi and put it on a pad, that works. Hydraulic lifts are all based off of hydraulic pressure, and we work on those. It can magnify a little bit of pressure to a lot of pressure for what we're doing. We can also do, so here's, you can do hydraulic systems. We can apply force onto a little piston. That same pressure is spread over the other piston, which will have it lift. And that device right there, that's a can jack. It's a nice little can jack that a lot of us have. Some of us have more than others. We ended up with a whole bunch of them at an auction one time. Very useful, but you don't normally think about ending up with a whole bunch of them that are out there. But that's going to cause things like stresses, and when we talk about stress fractures and looking at stress in materials, and this is where strength in materials come into play, because I can have a lot of stress where we get forces acting, and we can get compressive, and we can have things fail, and then we can get what we call moduluses of elasticity. How is it going to stretch? And we know what's interesting about this is that if I take a rubber band and we stretch it, it's going to go right back to its normal shape. Unless we overstretch it, right? And then we start getting deformation, and ultimately we break. Well, it turns out, doesn't matter what we have, there's an area, or there's a range of forces that I can apply the force to a metal bar, and it's going to go back to its original shape. It's going to be elastic. But eventually it's going to go to a place where I'm going to get deformation, and eventually it'll go to some place where I can get failure. And we actually can measure this for a variety of materials. They just show rubber, aluminum, and steel here, but polymers, this becomes a real important piece, and we can actually do tensile strength testing. And there's a lot of things that will affect tensile strength. And it is directional. If I have a carbon fiber, if I put it in a tensile strength apparatus like this and I'm pulling it along the fiber, carbon fiber has an amazing tensile strength. But even the lightest tap perpendicular to it is going to break it. Think about your mechanical pencil leads. That's exactly what's happening in a carbon fiber. That mechanical pencil lead is going to be able to stretch in one direction versus another. Everybody knows finger handcuffs, right? Everybody's played with finger handcuffs. Finger handcuffs, if I pull it apart, it's going to stretch out, and I've got my fingers tucked, but I have to go in, and you have to be kind of counterintuitive as to how you can get in and out of finger handcuffs. It's very, very similar for things like nanotubes and other structures that I can be very brittle in one direction and very, very strong in another direction. So I
read an article about nanotubes yesterday. They're changing the geometry and the angle at which the hexagons are laid out to try and increase the tensile strength of them.
Yep, there's lots of work on nanotubes, nanofibers, nanowhiskers. Carbon's one of those that if you get me in chemistry class and we talk about it's that one word. We get isotopes. You can. Well, they're not isotopes. It's just different structures. carbon has the most different structures. You can have the hardest substance that we know, which is diamond. You can have on the hardness scale, the softest substance that we know, which is graphite. So carbon can actually be used to cut things, and carbon can actually be used to lubricate. And you can do with the whole host of nanostructures, buckyballs. Carbon's amazing stuff, and no other element really can have as many different formations that carbon does. Sulfur's not bad, and phosphorus isn't bad. Sulfur and phosphorus have lots of different configurations as well, but not like carbon. I think sulfur has like 6, but not like carbon. But tensile strength, doing tests, and this is why strength of materials is really, really important. When you guys get into, you end up doing statics, and then we end up talking about strength of materials, and it's because the two go hand in hand, and depends on what the other thing that I don't know if they actually cover it in strength of materials, because I never actually took a strength of materials class, but I've ended up working with materials and looking at tensile strengths a lot, is that some of these properties will degrade via temperature, will degrade via exposure to ultraviolet light, particularly in the area of polymers. You end up trying to do heat stabilized polymers, you end up trying to stabilize polymers for UV degradation, you end up trying to stabilize polymers a lot. And so you play with the inner matrix to improve the various properties of the material. So if you were working in the polymer industry, we were doing strength of materials quite a bit. I worked with polyphenylene sulfide and polyethylene and polypropylene, looking at trying to improve the properties associated with UV. That you let plastics sit outside, and what happens to them?
They get brittle.
They get brittle. A lot of them get brittle. The other part that you work with is just how they're going to behave and with their heat capacity. Interesting thing about polyphenylene sulfide is it actually has a lot of characteristics like metal. It's a really cool polymer. It's a great polymer. And you can do a lot of different things with that one. So we have a lot of different aspects, and I'm going to wrap up because I could go through a bunch of these, and that's why I really want to make sure that you at least scan these chapters in the book, because he's giving you a whole host of information. And the idea is to introduce you to the various things that you're going to ultimately see throughout the course of your education. Some of you are going to focus more on certain topics than others. On the FE exam, you're going to get statics, you're going to get dynamics, you're going to get thermodynamics, you're going to get those basic electrical property things, because every engineer is supposed to have seen that, and that's why you get it on the fundamentals exam. But when you start going off and branching out, whether you're going to be a mechanical engineer or you're going to be somebody who works in environmental, as you can see, this problem that I gave you today is a potential to emit problem as an environmental air problem. And you're going, wait a second, it has nothing to do with air. It has everything to do with the material. But we do those calculations all the time from a variety of different things and looking at a variety of different processes. So you got to have some fundamental background in all the different aspects in order to have it work. So, we've got next week, week after. If you haven't come in to see me with your planner, do so quickly, because after Thanksgiving, the points for the planner will start to diminish greatly, and our final is going to be that week, the Tuesday of finals week. So, anybody got questions?